So just to recall, perfect squares will always do this. You'll always have the first one squared, the last one squared, and this one will be what happens when you multiply these two and double it. That's how it always works out. First one squared, last one squared, multiply these two and double it. First one squared, last one squared, multiply these two and double it. That is a perfect square trinomial. I'm pointing that out because we're going to use that to solve this today. When you're factoring a perfect square, it's always going to factor this way. If this is a perfect square, then these two will be perfect square roots, which they are. And then when you multiply those perfect square roots and double it, it should be that guy. And that's how it tells you that's what this is. So these three, we went from the squares to the trinomial. Here we go from the trinomial to the square. All right. So we just did solving by square roots, where you get the square by itself, like the x squared, and then you take the square root of both sides, and then you have your answer. And we did it actually with a binomial squared in your book. We take the binomial squared, take the square root, and then add or subtract whatever was inside the binomial. So what we're going to do in this section is we're actually going to create perfect squares. That way we can factor it to that group squared, and then take the square root of both sides and solve for our answer. All right? And so this is just another method. So the first method that we talked about was solving by factoring. We talked about solving by taking the square root. And this is actually going to be taking the square root, but we are completing the square to do it. We're making it a perfect square before we do it. And so they gave us this example. If we have something like this right here, a squared plus 6a equals negative 2. That's not going to be an easy thing to solve. Even if we bump it over, we're not going to be able to factor it. And so one of the things we can do is we can look at that left side and we can say, well, we have an a squared and a 6a. What would make this a perfect square? What you'll find is what will make it a perfect square is if you take this middle term, that's 6, and you cut it in half. So that's what they did. They take the 6, cut it in half, and square that guy. 6 cut in half is 3, 3 squared is 9. And add that to both sides, because whatever you do to one side of the equation, you have to do to the other. So on the left side, we're trying to make a perfect square, so we're going to add a 9. But since there's an equal sign, we can't add a 9 to one side. That balance just does this. We have to add a 9 to both sides to keep it balanced. Now what we have on the left-hand side is a perfect square, like what we had in our bell work. If we factored a squared plus 6a plus 9, it's going to be a perfect square, a plus 3 quantity squared. And now it's just like we did in the last section. We can actually take the square root of both sides, get rid of that square. On the left, we have just the a plus 3. On the right, 7 doesn't have a perfect root, but we can leave it plus or minus the square root of 7. And then to solve for that a, we just subtract the 3 over. So you'll see a equals that negative 3 plus or minus the square root of 7. You never would have been able to solve that by factoring. That's not possible, okay? So what you can do is you can solve it by completing the square. And so the process to complete the square is you're going to want to have the x squared and the ax squared and the bx by itself. And you're going to cut that b in half and square it. And then you're going to add that number to both sides. And you will have a perfect square every time you do it. So let's try one of those. Look at the next page. The only thing we're doing here is we're saying, what would you have to add to complete the square? Okay, so that's all we're doing at this point is just saying, what would you add to both sides to make this a perfect square? All right. And so we are going to look at the negative 16. So this is my ax squared. This is my bx. We're going to take the negative 16 and we're going to cut it in half. What is negative 16 if I cut it in half?
8.
Yeah, so we're going to get a negative 8. And we square that number. So negative 8 squared is 64. So to complete the square, to make that a perfect square, it would have to be x squared minus 16x plus 64. That would make it a perfect square. Now, if this were an equation, we would add 64 to both sides, but we're just doing the completing the square part. Because now if I were to factor this, this would factor to x minus 8. By the way, this is always going to be what we found here, squared. That's how I would factor that. X minus 8, factors of 64 that add up to negative 16. All right? And that's what we're going to do in this process. Look at this guy. This guy's not as pretty. He's a fraction. All right. So I'm going to take my b, that is 3/5. Dividing by 2 is the same thing as multiplying by what? 1/2. So if I have a fraction, as opposed to putting it over 2 like I did the 16, I'm just going to multiply by 1/2. When I multiply by 1/2, just multiply across. 3 multiply across 10. Okay? So that's what I'm going to take to square. I take this and I square it. Remember, when you square a fraction, you just square the numerator and you square the denominator. So the number that would make this a perfect square would be 3 squared, which is 9, over 10 squared, which is 100. And so the perfect square here would look like this: x squared plus 3/5 x plus 9 over 100. And if I were to say factor it, it's always going to be whatever this is, a positive 3/10. That's how that would look factored. Okay, so whatever you found when you cut it in half is what's going to be in your factoring. You've already figured it out because you're the one that created it. So we have this particular one. Now I will say, I'm giving you a one that actually I would probably solve by factoring if I were just handed this in like on a test and it didn't tell me how to solve, right? Because I could move that 9 over and I could say, okay, I'm going to plus 9 minus 1, etc., and I'm going to figure out what my answer is. But I'm going to show you an easy one with completing the square, and then we're going to do a couple more difficult ones with completing the square. So if given the opportunity, here's my go-to. If it's easy factoring, I'm going to very quickly factor, okay? If it's easy completing the square, like I have a 1 in front, I'm going to complete the square. And then we're going to do another one tomorrow called quadratic formula, which is actually my go-to if I can't very quickly factor it. I usually jump straight to quadratic formula. So we're going to do one that you can see is going to factor easily, but there are going to be some that will not factor and you won't be able to solve that way, okay? So for this one, we're going to do it by completing the square. And what we're going to do is we are going to do the process we just did, and we're going to figure out what would we need to add to this, okay? So when you are solving by completing the square, you do not want it equal to 0 necessarily. What you do want is you want the x squared and the bx, whatever this is, on one side. So if it had some number in it that was on this side of the equation, I would actually move that number over before I started the process. So for example, if I were completing the square for this and it originally said x squared plus 8x minus 9 equals 0, before I completed the square, I would move it over so it looks like this, okay? So when you're completing the square, you want that x squared and x by itself, and you want anything else out of the way on the other side. So to complete the square, I'm going to take this and I'm going to cut it in half, which gives me that 4, right? To figure out what I add to both sides, I square that 4. So what I'm going to do is I'm going to add 16 to the left side, and I'm also going to add 16 to the right side. It is an equation. I cannot add one thing to one side and not to the other, okay? So on the left side, my only purpose is to try to make this a perfect square. Whatever happens on the right is just, it's fine. Whether it's a perfect square, whether it's not, it doesn't matter, okay? And so now I'm gonna say, well, how would this guy then factor? Well, I already know because I created it. So this is always going to factor to an x, and whatever this is a positive 4, that's gonna be plus 4. This works out to whatever the addition works out to, 9 plus 16. It's gonna happen to be a perfect square as well, all right? And now, just like I did in the prior section, to get rid of a square, I take the square root of both sides. So I'm gonna take the square root of this left side, I'm gonna take the square root of this right side, all right? When I do that, remember, this left side, I just get rid of the square. On the right side, when I take a square root, I have to consider the positive and the negative root, right? So this is positive or negative 5. Yes? Now I have something I can actually solve. If this were like square root of 24, I wouldn't have had a perfect root. Square root of 17, I would just leave it as a root and move that number over, and I'd have this weird looking answer. But when it is a perfect root, like 5, I'm actually going to set up two equations, and I'm going to say, okay, x plus 4 could equal 5, and x plus 4 could equal negative 5. Those are my two options. And I'm actually going to solve for a whole integer here, like an actual number. So I'm going to subtract my 4 over, x could equal 1, subtract my 4 over, x could equal negative 9. If I had solved this by factoring, this little guy right here, it would have looked like this, which would have produced negative 9 and positive 1. That's what it would have produced had I solved by factoring. So you are literally solving these equations just as secondary way. But what's going to happen is I'm going to give you ones that I know you cannot solve by factoring. Okay, so I'm going to give you ones that I know are going to result in something that naturally you wouldn't factor, so that you know how to do this process. Because in life, if you handed me one I could factor, that's how I would solve it and I would be done, right? But it doesn't always give you these perfect, beautiful squares. So sometimes you have to have another method. This is the secondary method. So you're going to make sure that you have the x squared and the bx completely by itself, and whatever constant, bump him over to the other side. Take this b, this number that's in front of your x, cut it in half, and then square it, all right? Add that to both sides of the equation. It says factor. Your factor is always going to be the same. It's going to be x plus whatever this guy in half was, all right? Or minus if he's a negative. Apply your square root rule. If you have something squared and it equals a number, you take the square root of both sides. It equals the positive and negative root. And then solve. So if you have a plus or minus in there, which you will for these, actually subtract it over. I already have my 6 over to the left-hand side. I'm going to take my b right here, and I'm going to cut it in half, which is nice. 2 divided by 2 is going to give me a 1. 1 squared, well, that's just 1. So that means I'm going to add 1 to both sides. I'm going to rewrite this side with x squared plus 2x plus 1. And then I have the 6, and I also have to add a plus 1. To keep the equation the same, I have to add that to both sides. On the left-hand side, I already know how this is going to factor. It's always going to be x, and then whatever this is a positive 1, that's plus 1. That's how it's always going to factor. Over here on the right, 6 plus 1 is 7. 6 plus 1 is 7. And now we're just going to apply our square root rule. Our square root rule says to find this, I just take the square root of both sides. On the left-hand side, I have the x plus 1. On the right-hand side, I have the positive or negative root of 7. Does 7 have a perfect root? No, it is a prime number. I can't even simplify the root. If I could, let's say it had been 12. 12 doesn't have a perfect root, but I can simplify it, okay? 2 squared root of 3, okay? But I can't even simplify this. But I still need to solve for x. So my final step to solve for x here is to subtract the 1 over. All right, on the left, I now have the x by itself. On the right, those cannot combine. Negative 1 and plus or minus the square root of 7 are not like radicals. So your answer is literally going to just be left in this form. -1 plus or minus the square root of 7. That is your answer, okay? And you can see how you never would have been able to factor that, right? So -1 plus or minus the square root of 7. So if you have a nice, beautiful, even number in there, then when you cut it in half, you're going to have an even number and you're going to square it and it's going to be beautiful. If you have an odd number, however, and you try to cut it in half, you're going to get a fraction. All right? And so you are going to have to manipulate fractions a little bit when you do this. My process is the same. The first thing I need to do is get that 3 out of the way. So I'm going to add the 3 over. I can look at this and tell you that there are not going to be any factors of 3 that add up or subtract to give you 7. That's not possible. My only factors of 3 are 1 and 3. All right, so immediately I should see this is not factorable. So I'm going a different method. So I have a squared minus 7a on the left, and on the right I have positive 3. So now I need to figure out what I'm going to add. I'm going to take the -7, I'm going to cut it in half. That's what that looks like when you cut it in half. I personally am not going to do decimals here. All right, I'm going to leave it as a fraction. So take that and square it. Fraction squared is just the numerator squared, the denominator squared. All right, and so that's what I need to add to both sides. 49 over 4. It's hideous, but we're going to go with it, right? So 49 over 4 is not pretty, I gotcha, but that's okay. All right, here's the thing. On the left-hand side, you actually already know how to factor it. You just created it. So to factor this, while it looks absolutely disgusting, you already know how you're going to do this, because all this is ever going to factor is going to be your variable and whatever this was, all right? It was -7/2. So it's going to factor to a minus 7/2. That's your factoring. You don't have to sit there and try to figure it out. You created the perfect square. On the right-hand side, you do need a common denominator. All right, he is currently over 1. He needs to be over 4, right? So I'm going to multiply the top and the bottom by 4. That's 12 over 4. Everyone should know 12 over 4 and 3 are the same thing. All right, so I'm just adding 12 plus 49, right? That's going to give me 61. And I already know my common denominator is 4, okay? So far, so good? All right. So let's look at the next piece. The next piece says take the square root of both sides. So I'm going to take the square root of that, and I'm going to take the square root of this. On the left-hand side, a minus 7/2. On the right-hand side, all right, on the right-hand side, 61 does not have a perfect root. So that's going to be the positive or negative root of 61 over 4 does have a perfect square root. What is it? 2. All right. To solve for a, I'm just going to add that 7/2 over. All right. So there's a couple ways. They're going to write it a different way in your book. When you have that common denominator of 2, the other way to write it, you can leave it like this. That's fine. 7/2 plus or minus square root of 61/2. Or in your book, they probably did this. 7 plus or minus the square root of 61 over 2. Those are the same thing, right? If you have common denominators, you can add your numerators, so you can put it all under 1. Those two are the same answer, all right? But you'll typically see it written like that second way. This is typically how you'll see it written, all right? You won't see it written the other way usually.